If you've ever held a compass, you know that no matter how you turn it, the needle always swings back to point north. But why? What makes that tiny piece of metal so reliable? How does it know which way is north, even when you're in the middle of a forest, a desert, or out at sea with no landmarks in sight? The short answer is this. Earth is a giant magnet, and your compass needle is a small magnet that aligns itself with Earth's magnetic field. But the full story is much more fascinating. It involves electric currents deep inside our planet, invisible forces that stretch thousands of miles into space, and a moving pole that has been shifting for centuries. A compass is actually very simple. Inside it, there's a small, magnetized needle mounted on a pivot so it can spin freely. Like all magnets, this needle has a north pole and a south pole. Here's the rule of magnetism. Opposite poles attract. The north pole of a magnet is drawn to the south pole of another magnet, and vice versa. So when a compass needle points north, it's because the north end of the needle is attracted to Earth's magnetic south pole. Wait, what? That sounds backwards. It's not. The magnetic pole near the geographic north pole is actually a magnetic south pole because it attracts the north end of magnets. But we call it the north magnetic pole because of where it's located. This is one of the most common misunderstandings about how compasses work. Now, where does Earth's magnetic field come from? It's generated deep underground. The planet has a core made mostly of iron and nickel with a liquid outer layer. Electric currents created by the movement of this liquid metal produce a magnetic field that extends far into space. This is called the geodynamo effect. It's like Earth has a giant bar magnet running through its center, but it's actually much more complex than a simple bar magnet. This magnetic pole. This magnetic field has two poles, a north magnetic pole and a south magnetic pole. The compass needle aligns itself with the magnetic field lines, which run from the south magnetic pole to the north magnetic pole. These field lines are what your compass needle is actually following. But here's where things get really interesting. A compass doesn't actually point to the geographic North Pole, the point at the top of Earth's axis of rotation. Instead, a compass points to the magnetic North Pole. And that pole isn't fixed. It's not even at the same location as the geographic North Pole. Right now, the magnetic North Pole is in the Arctic Ocean, near Canada, about 1,000 kilometers or 620 miles south of true north. And it's been moving over the last century, drifting northward towards Siberia at a rate of about 60 to 80 kilometers per year. The difference between the direction a compass points and true geographic north is called magnetic declination. The declination varies depending on where you are in the world. For example, in most of Alaska, the needle points about 20 to 30 degrees east of true north. In other places, it might point west. Mariners and navigators use declination charts to calculate their true bearings. Without accounting for declination, you could end up miles off course. The compass was first invented by the Chinese around 1050 BCE. They discovered that lodestone, a naturally magnetized mineral, would always point in the same direction when allowed to float on water. This led to the development of the first compasses for navigation. By the 12th century, European sailors had adopted similar devices, and the compass became an essential tool for exploration. One of the biggest breakthroughs came in 1700, when astronomer Edmund Halley, the namesake of Halley's Comet, created the first magnetic declination chart, mapping how compass variations changed across the Atlantic Ocean. This was a game changer for navigation because sailors could finally correct their compass readings and sail with much greater accuracy. But there's a catch. The magnetic field isn't permanent. Over geological time, Earth's magnetic field has flipped many times. The north and south magnetic poles have swapped places. These reversals happen about every 200,000 to 300,000 years, though the timing is irregular. The last reversal was about 780,000 years ago. Scientists know this because they've studied the magnetic patterns recorded in rocks on the ocean floor. When lava cools, the iron minerals inside it align with Earth's magnetic field. When the field flips, the minerals record that flip. So what would happen if the poles flipped today? Your compass would still work, but the needle would point south instead of north. The magnetic field would become weaker during the transition, which could cause problems for satellites, power grids, and migratory animals that rely on the field for navigation. And speaking of animals, did you know that many creatures use Earth's magnetic field to navigate? Birds, sea turtles, salmon, and even some bats are able to sense the magnetic field and use it to migrate thousands of miles. They don't need a compass because they have tiny magnetic particles in their bodies that act like one. Now, here are a few more fun facts about compasses. If you used a compass in orbit near Earth, it would still align with the planet's magnetic field. But as you got farther away, the sun's magnetic field would eventually override it, and compasses can be fooled by metal objects, electrical wires, and even your phone. That's why it's important to keep your compass away from anything metallic when you're using it. Also, not all compasses work the same way. Liquid-filled compasses dampen the movement of the needle, making it easier to read in rough conditions. Military compasses often have luminescent markings for use in the dark. And today, of course, we have GPS, which can tell us where we are with incredible precision. But GPS signals can be blocked or jammed, and batteries can die. A compass never needs batteries, never loses signal, and never gets confused. So, why does a compass point north? Because Earth is a magnet. The compass needle is a magnet that follows its invisible field. But the north it points to isn't quite what most people think. It's not a fixed location at the top of the globe. It's a moving, shifting point hundreds of miles from true north. And that tiny difference has shaped navigation, exploration, and history for over 1,000 years. The next time you hold a compass, think about the incredible forces at work. A river of liquid metal flowing deep beneath your feet, generating a magnetic field that reaches far into space. A small piece of metal that aligns itself with that field, giving you a sense of direction no matter where you are. It's one of the oldest and most reliable technologies ever invented, and it works because of a process that has been running for billions of years.